Problem 84 is another example for using work energy equation. Here we have this mass, which is sliding on this bar. We are releasing it from rest at point A, and there is going to be friction between this mass and the bar. So it's going to slide down with the friction and hit this spring. The equation has two parts. First, what's going to be the speed of the mass when at the moment which is hitting this spring. Let's call that velocity v2. And also, what is the maximum deflection of the spring? So after touching the spring, it's going to compress it, then it's going to stop there, right? Which velocity at that point is going to be equal to 0. So let's solve both parts using work energy equation. To use the work energy equation, I'm going to need to know what is the friction force here. And to find the friction force, let's draw the free body diagram here for this mass. We have gravitational force mg, and there's going to be a normal force between the bar and the mass. Let's call it n. And also, because it is sliding down, we are going to have friction force, and the friction force is going to be mu k times n, because it is sliding. So the friction force must be equal to mu k times the normal force. And it should be against the direction of sliding. And if I call this direction x and this direction y, sum of the forces in the x direction must be equal to 0, because this mass is not moving in the x direction. Because of that, n minus mg times sine of 30 should be equal to 0. And m is equal to 2. So if you put the number here, n is going to be equal to 2 times g times 1/2, which is going to be g, or 9.81 Newton. So that's going to be the normal force. And by multiplying it to mu k, which is 0.4, we are going to find the friction. So the friction is going to be a constant force, which is equal to 0.4 times 9.81 Newton. And now I can use the work energy equation. Let's call this point 1, and the moment which is hitting the spring, let's call it 2. And because I have gravitational force or gravitational potential energy here, we need a reference line. You can put the reference line at any height you want. We can put it at the bottom, at the top. I'm going to put it here. And the work energy equation, T1 plus V1 plus U prime from 1 to 2 is equal to T2 plus V2. At the beginning, there is no velocity, so there is no kinetic energy. T1 is equal to 0. And V1, we have gravitational potential energy, which is going to be mgh. So it's going to be mg, and h, the height from here to here, is going to be 0.5 times sine of 60. And work of non-conservative forces. If you look at the free body diagram, mg is a conservative force. N and friction force, they are not conservative forces. N is not doing any work because all the time it is perpendicular to the direction of the movement. So we ignore N here. And the friction force, it is always against the direction of the movement. So the work of it is going to be negative. So we need to multiply that force, which is constant all the time, to the displacement, which is 0.5. So we are going to have negative mu k times N, or friction force, which we got it there, times the displacement, which is 0.5. It's going to be equal to T2, which is 1/2 of mv squared, and m is 2, plus potential energy, which is 0, because the mass is on the reference line. We know what is F, we know what is the mass, so from here we can find the velocity at this point. Velocity is going to be 2.56 meter per second. Now, the second part, how can I find the compression of this spring? So this mass is going to go a little bit more down. Let's say it's going to go down by x. So from here to here, which is going to be the compression of the spring, it's going to go down more by x. Now I can write the work energy equation between point 2 and this point, which I'm going to call it point 3, or we can write it between point 1 and 3. It's absolutely up to you. Let's write it between 2 and 3. So we are going to have T2 plus V2 plus U prime from 1 to 2 is equal to T2 plus T3 plus V3, and U prime from 2 to 3, because we are writing it between point 2 and point 3. The first time it is touching the spring, and point 3 is the maximum compression. So T2 is going to be 1/2 of mass times velocity at that point squared, which we got the velocity over there. And V2, there is no gravitational potential energy here, because it is just touching the spring. There is no spring potential energy too. So V2 is equal to 0. U prime from 1 to 2, we still have that friction, and also we have that normal force. The normal force doesn't do any work, but the friction is going to do more work, right? So we need to multiply that friction to x, and the work is going to be negative. So minus friction force times x. It's going to be equal to T3. At the end, there is no velocity because it is in the maximum compression. It means the mass is going to stop there for a moment before starting to go back, right? So there is no kinetic energy at that point. The potential energy, the gravitational potential energy, is going to be negative because it is below that reference line. So we need to have negative mg times the height, which is going to be x times sine of 60. It's going to go down. The height is going to decrease by x times sine of 60. And we have potential energy in the spring, which is going to be 1/2 of k, which is given, times x squared. Now look at this equation. We know what is velocity, so we have everything here. Friction force, we know it, and mg, we know it. So we are going to have a quadratic equation for x. You have x squared and also x in this equation. So after putting the numbers using your calculator, we can find x, which is going to be 0.0989 meter, or 98.9 millimeter.